Okay, hello everyone. And in this video, we will talk about analysis of a circular plate here. As you can see here on the screen, in the tutorial document, there is a circular aluminum plate and modulus of elasticity given to you, and the Poisson's ratio given, radius, thickness given. So theoretically, we should be able to calculate the deflection in terms of the load times the fourth order of the radius over d given here, and the Poisson's ratio. So now we can calculate that as 0.29 inches. So now let's work with Abaqus to say whether we can analyze this using plate bending elements here, so that we can um, compare the theoretical results with the analysis results here. So here, open you after you open the Abaqus, firstly, similar to what we did before, we create a folder where you can use easily. Here we have the tutorial 6. Tutorial 6. So we store everything here. So the first step, we create the geometry by using sketch, as shown in the, the document here. So we use the sketch, create approximate size. We maybe use 50 because that's diameter, or the diameter or radius. Our radius is 10, so we use 50. It would be, so we just create a circle. Create a circle, pick the center point, and we have the radius equal to 10. So this is what we have here, and we can click the cancel, click down. So we have the sketch created over here. So it's installed here. So that's a CAD file. Later on, we go to the part, create the part 1. It's 3D because it's noted formable. We use the shear. It's a planar. We just continue, and we load it from the sketch. So we are done. We're okay with that. We're done, and click done. So this is the geometry. We save the model. Here we have the circular plate created. Later on, we just need the property. We define the modulus of elasticity, hence sixth order Poisson's ratio. That's 0.3. So this is the material. Next step, define the section. So it's a shear section, it's homogeneous, and we have the shear thickness. So the plate thickness is 0.2 inches. 0.2 inches. We just use the 0.2 inches. So that's the same material. Thickness integration rule. Don't worry about the integration over here, and we should be able to find out the values here. Okay, and we assign the section defined here to the full region. So that's it. Next step, go to assembly, create an independent instance here. And we're done. Step, create a static general one. So everything is default. Go to the load. So we have all the exterior sides simply supported with a pressure equal to 10 psi. So we select displacement or rotations. So the boundary condition is that's interesting because simply supporting that means that we have uh, the z direction is restrained, and we also have the movement in the radian direction is restrained. But let's say how we define. So probably let's say what happened to the load. Just define the uh, rotation u1, u2, u3, and so this Cartesian diameter. So yeah, we can try that. So select the perimeter here. We just restring all the x, y, z direction. So that's simply supported over here, and then we apply the load. That's the pressure. So that's 10 psi. Because we have two sides, and either the brown side or the purple. Just select the brown one. So that's 10 psi. So if we take a look at the 3D view, so that's on the top view. That's on the top side because we have two sides. So now we do the mesh. We save everything. We wanted to show the XY only, and we do the mesh. I'm going to use element size 0.5. We use qual, the quadratic formulation. So we use that everything specified there. So we would like to use the quad shape, the quadratic formulation. So we use everything. So that means we use 8 load doubly curved cyclists here. And we define the element size as 0.5. And we do the control. We use everything as a quad. Everything is quad. Great. And then we do the mesh. So let's compare this with what the document show here. That's a little bit different here. But everything is quad. We may try remesh that so we can delete all the meshes here. Control this. We may try this one. Minimize the mesh transition. Remesh. Okay. So this is more similar to what we have in the document there. So save the mesh, then we submit the job. Create a job, then we submit the job. The plate analysis is very that takes a while. Remember that maximum displacement is 0.29. Okay, completed. So we can take a look at the results. Okay, we show the results. This is the stresses. We would like to show that displacement in the z direction. The maximum. Maximum value here. I think the maximum just show the maximum. Oh, that's 0. Show the minimum. That's point It's 0.8, and that's much lighter. Let's check what happened here. It looks like we use the same element size. We use element size as 0.5. Magnitude as 10. Section. Yeah, let's do a quick calculation here. So we have the W. Maybe something wrong with the calculations here. Use Excel to calculate that. So we have the R value, and we have the P value, and the D, the mu. So the D is equal to, we can calculate the E, the mu here, and the T, we have the D here. So we have the E equal to 10th order, and the T that's 0.2, mu that's equal to 0.3. So the D that's equal to E times thickness cubic over 12 over 1 minus mu square. So this is that rigidity. So that means we can calculate the displacement. This is equal to 10 psi. Radius is 10. So the W should be equal to P times 10th fourth order over 64 over D times 5 plus mu over 1 plus mu. So it should be 8.7 inches. I don't know what happened here. Maybe that the radius should be diameter. Maybe change that to diameter. That's not. So I think what we did is correct based on the equation here. So 8.7 inches instead of 0.29 inches. So probably I'm gonna update the tutorial. Something wrong here. Here we have 8.7 inches, very close to the theoretical value. So I'm gonna update the tutorial so that you will have the same numbers with this simulation here. I think that's all for this video. Good luck to your try, and I think that's this is the last video for our plate bending topic over here. Thank you.